Hey, we're back. Chapter 5 now, where we are going to learn about light. Okay, its properties, how it's created, and why do we do that? Because we actually want to understand how we measure the physical state of an object in space. We cannot touch those things, right? We already learned they're so far away. How did we learn they're far away? Well, guess what? It's all in the cosmic messenger or the light. And as we will also learn in this chapter, light is radiation, all right? Electromagnetic radiation, and we're going to emphasize this over and over again. Electromagnetic radiation. Anyway, I'm always happy to talk about something that I really treasure, which is the light. And it's also fun to teach this subject because you already know a lot about it. You feel it, you use it on a daily basis. You must be loving it too. Hey, you might be really looking forward to spending some time on a sunny place, like a beach, someplace exotic, where the sunlight really warms your soul up. So hey, speaking of warming up, you already got an important fact about light. Light that carries energy. It's important to state from the beginning some of the very important properties of light. All right, so light, known as radiation, carries energy with it. So Astro class, with this chapter, I'll try to give you a sense about how much light teaches us about the universe. But not before I discuss with you something really interesting, like how do we know about this speed of light? Remember that C from celeritas. This is actually, I forgot probably to tell you before. This C, the letter that is used for the speed of light, 3 times 10 to the 8 meters per second. Okay, that comes from the Latin for celeritas. It's speed in Latin. All right. So it's Latin for speed. Okay, celeritas. You got it. All right. So how did we actually learn that light travels so fast? So fast. So fast that we see, we get the message which is coming through light about everything that we see around us. It all started with Romer, Dutch astronomer or scientist. At that time, there wasn't really much difference between whether you're just studying life, you're studying things that exist and move around you. All right, so it says here about 350 years ago. So actually, Romer's experiments or notes on celeritas were from 1676. All right, so here's what Romer noticed. He looked up. He was looking at, so there are 4 big main satellites of Jupiter. I think I mentioned them in one of the previous lectures. And he actually measured just, kind of how long it takes for 1 or 2 or all 4 of them. It depends. They're not going, at the same pace, or they're not kind of tight with one another. So one at a time, how long, right? How long do they take to be basically eclipsed, to behind Jupiter? So they're basically eclipsed by Jupiter, these satellites. All right, and it turns out Romer measured that it takes a lot longer, okay, when Jupiter was further away from the Earth. Right? So basically it's the same phenomenon, right? So same phenomenon, but different duration. The only difference was different distance. And so Romer argued that this implied that light traveled at a finite speed. And he was actually able to calculate that speed based on these measurements. He knew the distance, right, between the Earth and Jupiter at different times, and he was able to time the duration of these eclipses, and he knew he measured basically all these distances and just some geometrical calculations, which I'm not going to bother you with, and he was able to find the value. We're not ever going to use this. There is actually not much point in using these many significant figures. So yeah, this is the value. This is 10 to the 8 as I have written it here. That's the speed at which light travels. All right. Okay, so now how fast light. The only difference, travels. Here are some more facts about light. So light carries energy. You can already feel that on a beautiful summer day, right? You get warmed up. Always travels at the same speed. So again, this can be very nicely written with scientific notation. So I have 3 times 10 to the 5 if you want the kilometers per second, or 3 times 10 to the 8 in meters per second. Again, units are very important. There are some two more interesting facts about light. Okay, so one is light is emitted and absorbed like a tiny massless particle, and that is the photon. Right? That is the massless particle. So there is a bunch of photons, basically kind of like pockets of energy. You can think about that, say pockets of energy, right? So localized light energy. So you can think of light as a photon, but in some other cases, light propagates like an unbounded continuous wave. So it behaves like a wave sometimes, and sometimes it behaves like a particle. And it took, physicists quite a lot of time and a lot of experiments and a lot of thinking to realize that, the properties of light and the behavior of light and the interaction with matter can be explained sometimes by a wave, sometimes by a particle, and then the quantum mechanics put actually them together, and that dual kind of schizophrenic behavior was put together by this quantum mechanics. But again, we're not going to get into that. It's just really interesting things to know about light. All right, so because as we will see, there are many kinds of light. We are actually able to measure some things about light to differentiate between those different types of light. So in what sense is light an electromagnetic wave? The light itself is actually a blend of an electric field that varies, right? So if this would be the intensity, the arrows of the electric field, it fluctuates, right? So it's like positive, it reaches a maximum and then becomes smaller and smaller, and then it fluctuates in the opposite direction. All right, and it keeps going. Then that's the direction of light propagation. Okay, so it's not just the electric field, as physicists have proved. Every time you have a varying electric field, that creates a magnetic field, and if any magnetic field varies, that creates an electric field. So they kind of create one another, and every time they meet, they basically give rise to light as we know it, right? So again, magnetic field fluctuates. So it does pretty much the same as the electric field does. So every time there is an fluctuating electric and magnetic field, basically light is created. All right, and so electrons or electricity, right? Electrons or charged particles move when light passes by, showing that it carries a vibrating electric and magnetic field. So in that sense, light is an electromagnetic wave. That's what light is. We see it as light. We gave it that name, but what actually happens there is a fluctuating magnetic and electric field. They fluctuate together. All right. So they do fluctuate, but they do fluctuate differently for different types of light. And it's very important to know, for example, like how long does it take for light to go from a full length, right? So you see, we have here, see the distance between two peaks. You see here, distance between two peaks, which, right, if you were to continue this, it would be exactly this, but you can measure that distance, right? When you go, not necessarily between two peaks, two consecutive peaks, you can measure that same distance between two zeros, right? Zero that come from the same direction, all right? So this would be just half of it. So anyway, that length, right? So that is the length, and that is the length of the wave. Well, therefore, that is going to have the name of wavelength. And that is usually called lambda. That's a Greek letter. Okay, so if that's the length, right, that's a distance, then that's going to be equal to speed, the speed at which that distance is traveled times the time, and that would be the period of the wave. All right, so what's the speed of the wave? Obviously that is c, and then the period, let's call it p. Okay, that's definitely the inverse of the frequency. Okay, the frequency is basically the ratio of time in which these peaks pass by, and so therefore p, this p, the period, is actually the inverse of the frequency, or the frequency is the inverse of the period. All right, so if we put these things together, then the wavelength is going to be c, the speed of light, divided by the frequency. All right, so this is frequency. There's a funny letter here that is nu, another Greek letter for the frequency. We can use f. Maybe you want to use f, the same thing. I think it's easier for you if you ask me, but you can insist, you can use nu as well for the frequency. All right, there is another very important thing that is associated with the wave. Well, that is the energy of the wave, and that is very much goes hand in hand with the frequency. So it's the frequency, but it's a constant here, a proportionality constant, and that is h. And that proportionality constant, so that's a constant, and that's actually Planck's constant, because Planck was the scientist who figured that out, right? So we have here very important, energy of the wave is h, which is Planck's constant times the frequency. So here are some important formulae which you're going to be able to practice with in your homework problems to basically differentiate between different types of light. Okay, speaking of which, right? What you see, say, coming from the sun or from the light bulb or some other sources of light in your life, that is the visible white light. And it's white light, you see it white, and it's visible because that's what your eye or your retina is sensitive to. But it turns out this white light is just a tiny part of the whole electromagnetic spectrum. And actually, this white light incorporates in it quite a bunch of different types of light. Okay, so Newton was the one to actually discover that this white light is basically a bunch of colors put together, right? So you can see the colors here. They're just transmitted through a prism in at different angles, right? So different colors, which are different types of light, are scattered at different angles. So basically the prism decomposes the white light into its components. So these are all components of white light. But can you actually believe, people took quite a lot of time to actually just believe Newton that this is actually what's happening, right? So you have white light coming in, and then you have a prism, and at the end of the prism you have the colors. So people said, oh well, no, it's just the prism that adds the colors. And so Newton thought about this idea a lot actually, and it took him about 4 years at least to prove that white light is made of many colors together, and that's not the prism that adds the color. So here's what he did. So he put all this experiment in a box, and then he let through just one of these colors at a time, right? So the way we did it here, so it was at some point it was this blue light, okay? And then he put a prism, and he said, okay, if the prism creates the colors, it should again create the colors. But here is what happened. So it was blue light, only blue light coming at the prism, and then it was scattered, refracted actually through the prism, and then it went away, and it was still the same blue light. So the prism did not and does not create the colors. So yeah, just another example of how not trivial it is to prove all these little things. So we know now that there are many types of lights, right? Of light. So there is the visible type. Our eyes are sensitive to, and then there are various wavelengths or frequencies or energies associated with them, right? So for example, the red part, this is low frequency or larger wavelength, okay, or low frequency or low energy within the visible spectrum. And then you have the blue, right? And this is the higher frequency and energy or lower or shorter wavelength. And it turns out, right, so in the meantime, ever since Newton came up with this idea that white light is actually made out of various types of lights at different frequencies or energies and wavelengths, we realized that this whole electromagnetic spectrum of light does not stop at the visible. It goes towards longer wavelength. So here's the wavelength. This is how it goes. So it goes longer here. You see how it's longer, right? The distance between two peaks. So that's the wavelength. And look at this one. It becomes shorter and shorter here, right? This is the distance between the peaks. This is the wavelength. So the type of light that it has longer wavelength than the red part of the spectrum, it's called the infrared, right? Infra for lower frequency, lower energy. So look at that, they're here. Frequency, energy, and this is how they become lower. This is the higher energy, higher frequency. And then you go to even lower frequency, lower energy than infrared, and you find the radio light, the radio type of electromagnetic radiation. And there are various types actually of radio. Starts with microwave, and then you go to centimeter radiation, and then millimeter, centimeter, meter radiation, and you get to the size. So lambda becomes the size of the football stadium. Now if you go in the opposite direction, so let's see, shorter wavelength than ultraviolet or UV, okay? Infrared is usually called IR, infrared. So shorter wavelength, that means higher frequency, higher energy, you go to ultraviolet, right? And then even higher, you move into X-rays, and even higher, you're gonna find the gamma rays. And this is a really nice diagram that shows you some examples of sources on Earth. Okay, for example, for the visible light, you're familiar with the light bulb. Sources of infrared, that's us or your pet if you want. Okay, again, sources of microwave, radio, obviously sources of X-rays will be the X-ray machines, that's what they create, and so on. And then we also have the cosmic sources, about which we are going to talk about for the next few chapters, and therefore the next 3 weeks. All right. So here are some examples of problems you're going to find in your homework and then the next exam. The question is, hey, the higher the photon energy, or the light energy if you want, light energy, then the longer or shorter its wavelength is, or there is maybe the energy is independent of the wavelength. We already know that is not true. The energy is H times F. Remember, this is Planck's constant. Let me tell you what that is. You can also find it. You can even Google it. But I think it is 6.626. I'm just going to give you the, more exact values so you can use it in your calculations in homework on mastering astronomy, times 10 to the minus 34 look at that power of 10, you're going to have to work with meter squared times kilogram per second. All right, so it's definitely energy dependent on wavelength, right? Because you might recall the frequency is actually c over wavelength. So let's put them together. Energy is going to be h times c over wavelength. All right, so that means higher energy, right? In order to obtain a larger number here, you need to divide by a smaller number here. So wavelength is going to be shorter, and you can see that in the previous diagram where they go in the opposite directions, right? So if the wavelength increases that way, then both the frequency and the energy increase in the opposite direction. Remember, gamma ray, X-ray, keep going, UV, and then here is visible, and then you get to infrared, and then radio, right? So that was the succession of the different types of light. So the higher the photon energy, the shorter its wavelength is going to be. The correct answer in this situation would be B. Hey, here's another question. Which type of electromagnetic radiation has a wavelength adjacent to but longer than UV light? So let's put it again on, say, the wavelength axis. Somewhere here is visible. All right, so adjacent to the visible but longer wavelength is going to be infrared, right? And then you move into radio. How about shorter wavelength or higher energy? Adjacent to this is going to be UV, and then you move into X-ray, and then the color doesn't really matter, gamma rays. All right, so adjacent to but longer than UV light. Let's identify the UV light. What's adjacent? It's either visible or X-ray, but we want a longer wavelength. So longer wavelength, that is going to be the visible. You go towards the longer wavelength. So this is how we answer questions like this. Here's another one. Which of the following statements is true of green grass? What do you think? So I'm just testing your knowledge or intuition here, because we didn't talk about this yet. So green grass, what do you think? A, it absorbs red light and emits green light. Or it absorbs red light and reflects green light. Okay, the only difference is in these two words. How about C? It transmits all colors of light except green. Or it means that the lawn is healthy. Okay, well, if you have been around JMU, you might have met the plastic lawn as well. So that will not have anything to do with the healthiness of the lawn. All right, so let's think about this. This one. C. It transmits all colors of light except green. Well, if it does not transmit green, how are you going to see it as green? So, can't see it as green if green is not transmitted. It turns out, as we will see, I think the very next lecture, that the grass, okay, the green grass does not emit green light. The correct answer for this question is B, and here are some examples of how these things work, and we're going to go into some more details in the next chapter. So, light interacts with matter, and it does it mainly by 4 processes. The light is emitted. Here are some examples. Sun or the lamp. So emission of light, okay? And that's usually white, although there are some lamps that can emit just 1 or 2 of the types that make the white light, all right? And then we have, for example, these green trees. They are going to absorb all colors except the green. What's going to happen with the green? It is scattered. It is reflected. Look at those arrows. So reflect the green component. The green component. Okay. The same happens here. So this red thing is going to absorb all colors except the red, and the red is going to be reflected, and that's why you see that thing red. The rose is maybe red because its petals are able to reflect the red more than anything. Every other component of the white light or the light that's coming from the sun are going to be absorbed. And the same thing here. Same thing. Same idea. Light is absorbed, and then some components or only one component is going to be scattered or reflected. Okay. Here's another thing that can happen with the light. The light gets to be transmitted. That usually happens with glass, right? All of the components actually go through. So all components go through. And the fourth one, the total reflection, okay, like the mirror here, all components are scattered, reflected. All right, so now you know why you're seeing all kinds of things in your line of sight every day and every minute.